right? So now you know the product rule, the thing that saves you so much time, and we're moving away from having to use those limits to evaluate derivatives. So now you get to also find derivatives of trig functions. We're just going to focus on cosine and sine today, and then as well as e to the x and ln x, right? So there'll just be some derivatives that you can add to your list to help you do it quickly and not have to use that limit notation. And I know you guys you already love remembering trig identities, so you just get to add that there, that same part of your brain as you did all this stuff last year, okay? So some things you have to remember, which I know you already have memorized, are these trig function review things, right? So you should remember that 1 over sine is cosecant. You should remember that cotangent is cosine over sine. I don't know why I have that one and not tangent. Tangent's the opposite of that, right? Tangent is sine, if you want to remember that. Tan x is sine x over cosine x. These three, how they're inverses, and then our favorite one, sine squared plus cosine squared, equals 1. Okay? So you're just going to have to remember those because they're going to help you evaluate different derivatives. But the two new things you're adding today are that if you have to find the derivative of sine x, it is cosine x. If you have to find the derivative of cosine x, it is negative sine x. The thing that is really cool about this is what this means is that if you make a graph of the slopes of the sine x function, if you make a graph of the slope of the tangent at every point, you would end up with a cosine graph. Isn't that really cool? It's a cosine graph is literally a graph of the slopes of sine x. I don't know, it's fascinating. And then same thing for cosine, if you make a slope of the graphs, if you make a graph of the slope of the tangent lines of cosine x, you would just end up with a reflected version of sine x. So I think I put that in here? I have the proof here. But you can also see the proof. Maybe I'll share that with you guys if you remind me in this lesson, because I might forget. There's proofs for these, but we're not going to go through them. But I just think it's really cool that the math works out that way. Okay? So here we're going to use these derivatives we're going to use these new derivatives that you've learned to evaluate these functions below. So the first example says y equals 3 cosine x. Find the derivative of y with respect to x. Okay, so first I'm going to use I'm going to rewrite this. This is my constant multiple rule. I'm going to rewrite it like this, right? I'm taking the 3 out, constant multiple rule. So dy, I'll write dy dx, equals 3 times the derivative of all of this, right? So this is the derivative with respect to y, equals 3 times the derivative with respect to x of cosine x. We're not deriving y on this side, there's no y. That's why that's not there. Okay? So now I know dy over dx equals 3 times, well, what's the derivative of cosine x? It's negative sine x. So this whole thing equals negative 3 sine x. You can also write y prime, which is what I'll do for the other ones. Show you the different notation. Okay, so number 2, if f of x equals negative 4 times sine x plus 9, what's f prime of x? Well, f prime of x is going to be equal to negative 4 times, what's the derivative of sine x? Cosine x. What's the derivative of a constant 9? It's 0, right? So f prime of x just equals negative 4 cosine x. All right, what if we have g of x equals 7 times sine x minus 3 times cosine x minus pi squared? Find g prime of x. All right, g prime of x is going to be 7 times the derivative of sine x, that's cosine x, minus 3 times the derivative of cosine x, that's negative sine x, minus the derivative of pi squared, well, that's just a constant, so that's 0. So g prime of x ends up being 7 cosine of x plus 3 sine of x, right? And just taking those two negatives and combining them. All right, now we have h of x equals cosine x minus pi squared over root 3 of x. Find h prime of x. Okay. So I'm going to do this. I'm going to rewrite this before I deal with it. So I'm going to rewrite h of x as this. Minus pi squared times what? This becomes times x to the negative 1/3. Right? I'm just moving the x to the top of that fraction. So now I can find h prime of x. What's the derivative of cosine x? It's negative sine x. Minus pi over squared is a constant, so it stays there. And what's the derivative of x to the negative 1/3? So this is your power rule. So I bring the negative 1/3 down, and then it's x raised to the negative 1/3 minus 1 and minus 1, which is negative 4/3, right? Minus 1. Okay, so now let's simplify all that. Equals negative sine of x, sine x. These two negatives now become positive, pi squared over 3. And then it's times, I can just write it separate, or you can combine these if you want, x to the 4th cube root. Right, that's what 4/3 means. So this is h prime of x. Okay, now let's talk about exponential functions. Okay, so graph of e to the x. You can draw it. I'm just going to look at this. If I can remember where e is. Here it is. Okay, there's e to the x, right? So just remembering, if you want to sketch what it looks like here, it passes through, the y-intercept is 1, right? And it has an asymptote at 0, and then it just kind of crosses there and goes up and up and up, right? That's the graph of e to the x. Okay, so if we made a table of points here, say x and y, if I evaluated this at negative 5, value 5, what does, I forgot my negative. Negative 5, what's the value of the function? The value of the function is 0.00673. Okay, what if I looked at negative 1? Oops. It's 0.0367, right? Okay. And let's think about that. What did we just do there? We plugged in a negative 1 for x. What we really just evaluated was 1 over e. Okay. What if I plugged in 0? Well, 0, we have e to the 0, which is 1, which is why it crosses the y-axis there. If I plug in positive 1, I have e to the 1, so that's just e. And then let's go to 2, where I have e squared. And I can use my calculator to check. What is it at 2? It's a 7.389, something, right? Okay, so if I look at this, the domain of e to the x is all numbers, right? Negative infinity to infinity. But the range is there's a horizontal asymptote at 0, but then it keeps increasing. Right? So you have to remember what this graph looks like. Okay? And I'm just going to also write these things here in case you forgot these. Like if you have to do that, your exponent rules, when you multiply the exponents, they have the same base, you can add them. Remember this in case you forgot this stuff, because you might need it in your work today. So again, the really, really cool thing about the graph of e to the x is that when you differentiate it, the derivative of e to the x is e to the x. So when you make a graph of the slopes of the tangent lines at every single point along this curve, you end up with the exact same graph, which is really cool. So here, if you open the electronic link to the notes, you'll see that you can see the proof, which is really cool. And you can also think of it, right? Like here, as it starts flattening out, the slope is getting close to 0. And apparently, if you think about it, the value of that slope that's getting super close to 0 is exactly the value of the graph, right? And here, the slope at y equals 0 is exactly 1, the slope of that tangent line. So it's pretty cool. So just remembering what the graph looks like, and now we know when if you ever have to take the derivative of e to the x, it's just e to the x. Watch the proof if you want to see why. So let's do some examples. So f prime of x, if we have to find the derivative of 3 times e to the x plus 4, I know I can keep my 3 there, constant multiple rule. The derivative of e to the x is e to the x. The derivative of 4 is 0, so this is the derivative. I don't need to write plus 0. I'm not going to do that. All right, here, what if the function is 15x squared plus e to the x? Well, let's deal with this part first. Derivative of 15x squared is going to be 30x, right? 2 times 15 is 30, and minus 1 is just 1. Plus, what's the derivative of e to the x? E to the x. I don't think those are too hard. So the last one today is to find the derivative of ln x. So if you have to find the derivative of ln x, the derivative is 1 over x. Again, I put a link if you check out the e-file for the notes where you can see the proof of why this is. All this stuff is really fascinating about how when you make a graph of the slope of the tangent lines of a function, it comes out to an exact other function. It's really cool. So, and then here are some rules you'll have to remember if you're dealing with ln rules. So remember, if you have ln and then x raised to a power, you can bring the power to the front. If you have ln x times y, you can separate them with a plus. Division is minus. This is the last thing we did in pre-calc last year, so hopefully it's fresh in your mind. So if y equals 3 times ln x, then y prime equals, I still have my 3 there because of the constant multiple rule, and then the derivative of ln x is 1 over x. So then the whole thing is just 3 over x. Here, y prime. So this is supposed to say ln of 5. It's a typo. Add that ln there. So this, no, I'm taking this back. This is supposed to be like this. That's how I wanted to write it, so we can use this rule, okay? So we're gonna do it that way. So then y prime would be what? Well, I'm gonna rewrite y first as ln of x minus ln of 5. Now I can find y prime. The derivative of ln x is 1 over x. The derivative of ln of 5, that's just a constant, so that's 0. So y prime is 1 over x. All right, here we have y equals ln of x squared. So I'm going to use this first rule. I'm going to rewrite y as 2 times ln of x. So then when I find y prime, it's just 2 times 1 over x, which is equal to 2 over x. All right, here, let's rewrite y first. So the first thing I know is that I can take this 4 out and write it as 4 ln of 5. X, almost forgot that part. And then now this is a product, so I'm going to use this second rule. So y equals 4 times ln of 5 plus ln of x. So then y prime is equal to 4 times the derivative of ln of 5, that's just a constant, plus the derivative of ln of x is 1 over x. So then y prime is equal to 4 over x. All right, hopefully that wasn't too challenging, just adding some new derivatives to your memory, to your toolbox in your notebook. Okay, bye.